Okay, so we're going to take a little bit deeper look at acids and bases and equilibrium constants for those guys. First thing that we need to point out is a couple of reminders from Chem 20. So first of all, we know that strong acids, that there are 6 of them, and we know that strong acids ionize 100%. And so because they ionize 100% in water, there's no equilibrium that's established. This is the same for strong bases as well. So strong acids and strong bases do not form an equilibrium reaction in water. It's just, here's what I put into water, it separates into these things, all of this turns into all of that. There's no back and forth, no forward and reverse reaction. And so if we were to do a simple calculation with this, because strong acids, in this example, ionize 100%, then if I'm asked to calculate the pH of hydrochloric acid, that has a concentration of 0.172 moles per liter, then I can easily do this. I know that the concentration of HCl is going to equal the concentration of H+, because 1 mole of this is going to make 1 mole of H+, and so the concentration of H+ will be the same, 0.172 moles per liter. I can take the negative log of that, and I end up with a pH of 0.764. And so these are calculations that we did in Chem 20. Everything from here up is Chem 20 stuff. And just a matter of really simply using those formulas. Where things start to get tricky is when we're talking about weak acids and weak bases, because the fact of the matter is because weak acids and weak bases do not ionize or dissociate 100% in water, they are going to form an equilibrium reaction where we have a forward reaction and a reverse reaction for that. And so you can see one example that I've got here for this weak acid. This is vinegar. This is CH3COOH. If I place it into water, not all of it is going to turn into the acetate ion and hydronium. You can see that because this acid is an acid, it's going to make hydronium in water. This is a little bit of Arrhenius theory that we talked about last year in Chem 20. This hydrogen ion gets donated to the H2O, making the acetate ion and the hydronium ion over here on the product side. And I can write an equilibrium expression for this. So the Kc of this acid is going to be this expression right here with those concentrations. This is aqueous here, right? All my states of matter in, and so I've got the acetate ion and hydronium on the top, the products, and then my reactant on the bottom. Notice that I do not put in water in this equilibrium expression, and it's because water is a liquid. Now, because this is the Kc of an acid, and because we deal with acids and bases a lot in terms of solutions, just like for our previous video of the ion product of water, they also give the Kc of acids a special symbol. And so instead of calling it the Kc of acids, they just call it the Ka. And so the Ka, it's still an equilibrium expression, it's still an equilibrium constant, but it's the constant for that particular acid. And the Kas are always expressed with that acid mixed with water, okay? Now for weak bases, the same is true. I have this weak base. It's not going to ionize 100% in water or dissociate 100% in water, and so because of that, it's going to have an equilibrium constant. It's got a forward and a reverse reaction. We can have the Kc expression here. Here it is written down below. You can check my work, make sure I did it correct. But again, this K value is not called Kc. If this is the equilibrium expression for a base, then we call it Kb. And so what I can do now is I can take, if you look over here on this little spot right here, I can take, if I take this Ka value and I multiply it with this Kb value, just take these expressions and multiply them together. You can see that I've done that. Here's the Ka multiplied by the Kb. You can see that I've got the acetate ion concentration on the top and the bottom, and those would be the same numbers, and so I'd cross them out. These numbers here, also the same numbers. And so multiplying the Ka and the Kb cancels everything out except for the hydronium ion concentration and the hydroxide ion concentration. And so if I've got these two numbers being multiplied, this is all I've got left from the canceling out up here. Hydronium ion concentration times the OH minus ion concentration, you remember from the previous video, that equals Kw. And so what I can say now is that when I multiply the Ka times by the Kb, that equals the Kw of water. And so this is another formula that you guys need to add to your formula sheet. It's not one that is given in your data booklet, so it is one that you should probably spend some time memorizing. It's a pretty simple one there, so I think it's pretty easy, but that's the relationship between Ka, Kb, and Kw. And what you can now do is if you're given a Ka for an acid, you can calculate the Kb for its alternative base that it turns into. We'll explore this concept a little bit more in future videos, but as long as you've got this relationship down and you understand, okay, Ka times Kb equals Kw, then that's all you need to know for right now. In the next clip, I'm going to do an example where now we're calculating the pH of not a strong acid, but we're going to calculate the pH of a weak acid. And for just comparison's sake, we're going to use the same concentration. So I'll have that example up here on the board. Hang tight with me for a few seconds, and we'll get started on that example. Okay, so here's this example that we're going to talk about where I said that we're going to calculate the pH of a vinegar solution, acetic acid, with a concentration of 0.172 moles per liter. Now, if you remember, the concentration of hydrochloric acid with this concentration yielded a pH of 0.7 something. It was really, really small. What we would expect is, because this is a weak acid and only ionizing a very small percentage, that the concentration of hydronium here would be a lot smaller, which would then yield a much higher pH. And so we're going to do this calculation, we're going to figure this out, and hopefully that rings true from what we expect. So here's the equilibrium reaction, and in order to do these questions, you got to do an ice table. And so we've learned about ice tables and how they function, and this right here is the initial acid concentration. So this 0.172 moles per liter. Before the reaction begins with water, this is going to be the initial concentration, 0.172 moles per liter. Now, if this was a strong acid, all of this would turn into this, but it doesn't. It's an equilibrium reaction. So we've got a change here, which is going to be a negative x, and however much this changes by, this is going to gain that much. So these ratios still hold true. So plus x and a plus x here. And so my equilibrium concentration is going to be 0.172 minus the x. That's whatever this calculation is going to be, that's my equilibrium concentration for that. And this is just 0 plus x, which just gives me x. And this is 0 plus x, which just gives me x. For the ice table, you'll notice I've scratched out water, and the reason I've scratched out water from the ice table is because water is a liquid and it's not in the Ka expression for this. So I write the Kc expression, or Ka expression, as it is for acids, and I get my products on the top, so x times x divided by my 0.172 minus x on the bottom. And so if you look at this, this is just x times x, which is x squared, divided by the same thing. And this is the Ka value, and the Ka value comes from the data booklet here on your acid-base chart. And so I bring this up a little bit closer. You can see that acetic acid is right here. You just look over on the very right-hand side in the Ka column, and you can look up Ka values for particular acids that you'll be working with. So this one is found in the data booklet. So the Ka is 1.8 times 10 to the negative 5, and that's equal to this right here. Now this is a problem because if you look at this, this is a quadratic equation. Now the nice thing about Chem 30 is that they do not require you to use the quadratic formula to solve any problems here. And so if you run into this situation, there's an approximation rule that you need to follow. Now, if you want to read what the actual approximation rule is, you can read that on the bottom of the acid-base chart here. It's where it says note, and you can read that. It's kind of complicated in my opinion. This is sort of Mr. Orr's terms of what the approximation rule is, and here it is. It says that if the initial acid, Ia just stands for initial acid, if the initial acid concentration is at least 1,000 times larger than its Ka, then you can use this approximation rule, which is that you can ignore negative x. So if I come back over here, here is the negative x. All this is really saying is that because the Ka is so small compared to the initial acid concentration, the change here is, like, if this is such a small number, the reactants are highly favored in this equilibrium. And so this change here is so small that it really has a negligible effect on the calculation of this number. So really this equilibrium concentration is going to be very, very, very similar to 0.172 moles per liter. So the approximation rule again is if the initial acid concentration is at least 1,000 times larger than the Ka, then you can ignore negative x. In other words, you can just erase it. It's out, and I don't need to have it in my calculation at all. So now this calculation becomes a lot easier. Now I've got just x squared divided by 0.172, and that's equal to 1.8 times 10 to the negative 5. So if I plug all the, if I rearrange this to solve for x, x is going to be equal to, x squared is equal to 1.8 times 10 to the negative 5. I should write this other one in. I'm going to multiply that number over, so this is 0.172. Right there, this is moles per liter, and then my Ka value 1.8 times 10 to the negative 5. Oh boy. Now to get x instead of x squared, because I want to solve for x, x is equal to, I just take the square root of both sides like this, so it's the square root of 0.172 moles per liter times 1.8 times 10 to the negative 5. Now, I can plug this into my calculator, and I get 0.172 times 1.8 times 10 to the negative 5, and that gives me x is equal to 1.76 times 10 to the negative 3 moles per liter. Now, what do these numbers mean? Well, this number is x, which means the number I care about if I want to calculate the pH is the hydronium ion concentration. And so I take 1.76 times 10 to the negative 3 and plug it in for x, which is this equilibrium concentration right here. That is the concentration of hydronium in this solution when it reaches equilibrium. And so that's the number I want to use to calculate the pH. If you remember the pH formulas, pH is equal to the negative log of the hydronium ion concentration. I just take this number, plug it into this, and I can take the negative log of that, and that gives me 2.755 as my pH. And that pH is, in fact, larger than the one we calculated in the previous clip for hydrochloric acid, which makes sense. A strong acid with the same concentration is going to have a lower pH than a weak acid with the same concentration, simply because strong acids ionize 100% and weak acids ionize less than usually 1%. And that is the case here for vinegar. Its Ka value, you can see, is very, 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 very tiny, and so this is a very highly reactant side favored reaction, and that's why we get that answer. So I'm going to be right back. I'm going to show you how this problem can be done in a lot shorter way. So hang tight with me, I'll be right back. Back again with this example. We've got the work here that I showed previously, but what I wanted to show to you was what each number really represented. And it turns out that you really don't need to do these ICE tables to figure out these problems. Here's when you can use, well, let me show you the shortcut first. So here's what we ended up with all of our calculations here. And the calculations, really, there's not a lot of them, but there's a bit of work here that we can eliminate if we need to. So X we established represents the concentration of H3O plus hydronium ions at equilibrium. And so I've put that here. Right here, 0.172 moles per liter, that is the initial acid concentration. So I've put that here. And the 1.8 times 10 to the negative 5 is the Ka value for that particular weak acid. So I've put that here. And so this is the formula that you can use, and this is for any weak acid that you can use to calculate the hydronium ion concentration. If you have the initial acid concentration and the Ka, you can calculate the hydronium ion concentration for a weak acid. Couple things to note. First of all, you can only use this formula if the approximation rule is being followed, okay? You cannot use this formula if your initial acid concentration and your Ka are not 1,000 times different from one another. Second thing, this is a formula that can only be used for weak acids. We don't want to use this formula for strong acids because if you look in your data booklet, the Ka for strong acids just says very large. There's no number there that it gives you, so you really can't even use this formula for that, although there are some kids who try. So don't try to use this formula for strong acids. Now, you might ask yourself, well, what about weak bases? I can use this for weak acids, that's great. Can I use this formula for weak bases? And the answer is yes, you can, but it's going to calculate things a little bit different. Remember, in our previous example, we talked about this equilibrium reaction for Kas, and we also talked about an equilibrium reaction for Kbs, or weak bases. And so if you've got that reaction here, you're going to have hydroxide over here, not hydronium, which means this is not going to be hydronium, this is going to be hydroxide. You'd be calculating the hydroxide ion concentration. And you would use not an acid concentration, but you would use the initial base concentration because it's an equilibrium of a base with water, not an acid. There wouldn't be an acid present. So you'd have to use the initial base concentration. And then because it's a base, it's not going to have a Ka, it's going to have a Kb. And so you have to make sure that you're using the Kb for that base in order to use that formula. And then if you were asked to calculate what's the pH for this base, then you'd have to remember when you take the negative log of this number, the hydroxide ion concentration, that's going to give you a pOH value, and then you're going to have to convert that into a pH number. So there's a couple things to watch out there. Watch out for when you're using these formulas, but they are very helpful in terms of limiting the amount of work that you have to do, and you can come up with some answers. Now, one other question that I get often is I get asked, well, what if I'm given the hydronium ion concentration and the initial acid concentration, and they ask me to calculate the Ka? Can I use this formula? And the answer is, it's a good idea not to, because the problem is that if the Ka ends up being less than 1,000 times larger than the initial acid concentration, when you use this formula, you are assuming that it is 1,000 times larger. And so if it actually isn't, you're making an incorrect assumption, which is then going to yield you an incorrect answer. So you need to make sure that if the question is giving you the hydronium ion concentration and the initial acid concentration, and it's asking for you to calculate the Ka, then you do need to use an ICE table for that, figure those things out, calculate them, and just come up with the Ka using the Ka expression and calculating those numbers there. So one more example that I'm going to show you is that specifically, how can you use the ICE table to calculate a Ka if you're given the hydronium ion and the initial acid concentration, so that all loose ends are kind of tied up and you know all the different types of questions that you could be asked. So one more example, be right back, hang with me. Okay, so the question that we're going to go through is number 70 in your practice diploma booklets. And so I've kind of tried to write out what the question was on the board and show you what was given to you in the question. Essentially, it says that we've got an initial concentration of this weak acid called anthocyanins. And prior to equilibrium, its concentration was this, so that's its initial concentration. This balanced equation you can see in the question is given to you in the question. And so I've just created a nice table here to kind of fill this in. Now you'll notice that the question is asking for us to calculate the Ka for this equilibrium reaction. And it does give us the hydronium ion concentration. It gives us 8.5 times 10 to the negative 4 moles per liter. I know that it goes here in the equilibrium row because it tells me in the information box that this is the concentration of hydronium at equilibrium. And so I kind of forgot to mention that up here in my problem up here, so that's why you kind of see it written in small letters up above. So what I'm doing is I'm illustrating to you that you can't use that little shortened formula to avoid an ice table in these types of circumstances, because you aren't given the initial acid and the Ka to compare them to see if they fit the approximation rule. And so you have to do the ice table to figure it out. Now the math here is not difficult. It's actually fairly simple, but you do need to do the ice table in order to get the correct answer. So if you take a look at this, I've got my initial acid concentration here. My initial concentrations for my products are 0, simply because when the reaction hasn't begun yet, I'm going to have nothing over here on the product side. Then my negative x and my plus x over here. Now I know that this 0 plus x has got to equal this, so I know that x is equal to this number. So now I can start to substitute numbers in. That means that I know that this number is also that number. And I know that this is x, which means I can put this in for my negative x and calculate what that number is. So I've written my Ka expression here. You can see that, my products over my reactants. And you can see that my x times x is just going to yield an 8.5 times 10 to the negative 4 squared. And then I'm going to divide that by this calculation right here, which is my reactants, my equilibrium concentration of my reactant that's in this Ka expression, which is the concentration of A+, this anthocyanins. So 1.62 times 10 to the negative 3 minus 8.5 times 10 to the negative 4, which is the x in that formula right here. And so I plug this into my calculator. I should get this number on the top, 7.23 times 10 to the negative 7, divided by 7.7 times 10 to the negative 4 on the bottom. And I plug that in, and I should get 9.4 times 10 to the negative 4 as my Ka value. So that's how you can calculate Ka for examples like this. Couple of things to watch for. Hopefully it was clear. If you had a little bit of trouble with some of the things, don't be afraid to rewind the video and watch it again, and hopefully it helps a second time. Thanks everybody for watching. See you in the next one.